From this video, you will get a high-level overview of the new decompaction capabilities in version 8 of StructureSolver. We're excited about these new capabilities, which have taken time and technical care to develop. We believe that they will be useful to you if you work in salt basins or other complex environments. As you know, when sediments are buried in a basin, they undergo compaction as pore waters are expelled. They are often folded and faulted at the same time. To understand the evolution of a sedimentary basin, we try to recreate the configuration of sedimentary units at various points in the past. This entails reversing the effects of faulting and folding using methods of structural restoration and transformation, and reversing the effects of compaction through quantitative decompaction. In this example, we have restored and decompacted an interpreted seismic section across a salt diapir using StructureSolver's restoration and decompaction workflow. The result is a sequence of frames that reconstructs the development of the diapir and surrounding sediments through time and provides estimates of paleowater depth based on Airy Isostatic balance. We animated this sequence using screen recording and video editing software. The animations first show the basin and diapir development forwards in time, and then in reverse order from the present day. StructureSolver's methods for dealing with decompaction differ significantly from those used in other systems in ways that we believe benefit you as a geologist. Here are some of the key features of our approach. Seismic data. Whenever seismic data is available, we carry the seismic data throughout the entire workflow, as you have seen in the previous clip. This allows you to gain insights and validate results in a direct manner in comparison to workflows that use line drawings of geological sections. Use of structural components. We implement restoration and decompaction for individual structural components rather than for entire sections. Individual structural components are typically bounded by major faults, salt boundaries, or welds, but may have minor internal faulting. You can very flexibly define structural components and group them together. You can restore and decompact suprasalt and subsalt components one by one, and then rearrange the final components to account for salt mobility. Restoration before decompaction. In some systems, decompaction is performed prior to restoration. This approach is possible in StructureSolver, but we advise you to perform restoration prior to decompaction instead. The advantages of our preferred order are as follows. First, restoration transforms the paleodepositional surface into horizontality and underlying strata into their correct horizontal positions at the time of deposition. Thus, decompaction can be performed vertically. This approach is particularly important for structures that are steeply dipping, and even more so for overturned structures. Secondly, restoration of a structural component that has internal faulting removes the faulting of the paleodepositional surface and the underlying beds, again allowing decompaction to proceed correctly. In contrast, decompaction before restoration is intrinsically unreliable for steeply dipping and internally faulted structures. Single-step approach. In theory, StructureSolver could incrementally restore and decompact in small successive steps, starting with the youngest paleodepositional horizon. For example, you could produce a 5 million year state starting from the present day state, and then a 10 million year state starting from the 5 million year state, and so on. In principle, this approach would closely reverse the coupled effects of structural development and compaction. However, this incremental approach compounds errors if there are any inaccuracies in intermediate states. Thus, we always start from structural components in their present state when producing restorations and decompactions for a particular depositional horizon. We have found that single-step restoration and decompaction on a horizon-by-horizon basis typically produces very similar results to multi-step restoration and decompaction, but with much cleaner results. Once a restored structural component has been decompacted, it cannot be decompacted a second time. However, a decompacted structural component can be further transformed in order to add a bathymetric profile, for example. Layer-dependent decompaction. We assume that the compaction of a specific sedimentary lithology can be described using a compaction curve that describes the variation of porosity as a function of burial depth, independent of other factors. Compaction curves are typically estimated from well porosity logs. In StructureSolver, compaction curves can be assigned on a layer-by-layer basis. You can also specify spatially variable compaction curves that allow for compaction behavior to vary laterally within a sedimentary layer. StructureSolver has robust capabilities for managing porosity logs and fitting compaction curves to porosity data using a variety of curve types. Compaction curves can be easily assigned to horizons using the interpretation dashboard. Workflow. We have developed and documented a systematic workflow for restoration and decompaction of structures in salt basins consisting of 13 well-defined phases. The workflow is supported by a comprehensive set of warning and error messages to help you avoid or resolve problems. As is typical in StructureSolver, all operations are undoable, and you can instantly transfer curves between states. Please see our workflow video or the StructureSolver documentation for more information. Speed. Decompaction is a highly computationally intensive operation, particularly when dealing with seismic data. We put a lot of effort into computational efficiency, including comprehensive use of parallel computation on modern multi-core PCs and laptops, similar to those that you might use. As a result, decompaction can be performed almost instantaneously in many cases. With these new features, you can now perform restoration, decompaction, and isostatic adjustment of interpreted seismic sections in areas of structural complexity, such as salt basins. These operations can be performed at the speed of thought, thereby allowing you to rapidly gain insight into salt diapir growth, depositional environments through time, and trap formation. We hope that you find these new capabilities useful in your work.